Okay, so this is question 1 from the second review packet, and it deals with limits. It doesn't say we need to use any special method here, so anything that makes my life easier, I'm going to try to apply that in this case. All right, so we're taking the limit as x approaches infinity, which what we would like to do then is divide each of the terms in this expression by the highest degree of x of the denominator. So the next thing I'm going to do here is just rewrite this as the limit as x approaches infinity of 2x cubed, and I'm going to say over x cubed, and that's because that's the highest degree of x in the denominator, plus x over x cubed, and I'm going to do the same thing with each term in both the numerator and denominator. So some great things are going to happen here. Obviously, the degree of the denominator is greater than the degree of the numerator in this case, so that's going to go to 0. In that case, that one's going to go to 0. We've got one here that's going to go to 0, 0. This will go to 0, but we do have two terms here that won't go to 0. So essentially, this is the same thing as the limit as x approaches infinity of, I have 2 because I've got some cancellation there, plus what is essentially 0 and 0 divided by, I've got a 0 minus a 0 plus a 0 plus 7. So at the end of the day, this limit is equivalent to 2/7. Example B. So I want to think about what's going to happen when I plug in this 0. I'm taking the limit as x approaches 0. So what is tangent of 0? Well, that's going to be 0. And 0 squared plus 0 is 0. So this gives the form 0 over 0, which is indeterminate. So I'm going to try to use L'Hopital's rule here. So let's do that. So I have the limit as x approaches 0 of, I need the derivative of the numerator, and that's a chain rule. So the derivative of tangent is secant squared, but I also need to multiply that by the derivative of 3x over 2x plus 1. So now let's evaluate this thing by plugging in the 0. So that's going to be 3 times secant squared of 0, 3 times 0 is 0, over 0 plus 1, right? 2 times 0 plus 1. All right, so secant squared of 0, and you're probably thinking about secant in terms of what that means for cosine, right? This is the same thing as 1 over cosine squared of 0. And cosine of 0 is 1, so this is 1. So I have 3 times 1 squared, which is 1, over 1, which is 3. Okay, and now for problem C, let's just take a look at what's going to happen here. I think it would be easy to look at this, just to rewrite it real quick, as the limit as x approaches infinity of x squared over e to the 3x, deal with that negative exponent. All right, it's nicer to look at it this way too because of what's about to happen. So if I think about each of these two functions, x squared and e to the 3x approaching infinity, I'm going to end up with something in indeterminate form because my numerator is going to go to infinity, obviously, infinity squared. And then e to the 3x, that's going to go to infinity as well as that exponent grows exponentially larger. So I've got one of those indeterminate forms, infinity divided by infinity. So it's indeterminate, and I'm going to use L'Hopital's rule. Okay, so this is now the limit as x approaches infinity of, and the derivative of x squared is 2x. The derivative of e to the 3x is e to the 3x, but the chain rule says that I have to multiply that by the derivative of the 3x, which is just 3. Okay, so what's going to happen here if I plug in infinity? Well, we're going to have infinity and infinity, so we're going to have to apply L'Hopital's rule again. Limit as x approaches infinity of, now it's 2 over 9e to the 3x. And so this time our numerator is not going to go to infinity. Our numerator is just 2. But as the denominator goes to infinity, this whole thing is of course going to approach 0, because when the denominator is growing exponentially and the numerator is staying the same, we're approaching 0. Okay, in problem number 2, we're just taking derivatives. So we're going to use a lot of our different derivative rules, and it's important that we remember not to simplify. You're going to be tempted in a lot of cases to spend time making these look nice, but you don't have to worry about that. All right, so here I am seeing a product rule where I would consider my f function to be x squared and my g function to be 1 plus x to the 3 halves. So then f prime is easy, that's 2x, but g prime, there's a chain rule there. G prime is going to be the derivative of the exterior function, which is 3 halves, 1 plus x to the, and then 1 less than 3 halves, which is 1 half, times the derivative of the interior function, which is just 1. But don't forget, we did apply the chain rule there. So we don't need to put the 1, but we should consider that because it's not always going to be 1. Okay, so let's use our product rule then. So f prime of x then is g times f prime plus f times g prime. Okay, and remember, we don't have to simplify this. This is correct, actually, right here. So let's just leave it like that. But while it wouldn't be simplifying, a nicer way to write it would be the square root of 1 plus x cubed with 2x in front plus 3x squared radical 1 plus x over 2. But you're just fine leaving it like that because that is correct. All right, example B. This is obviously going to be the quotient rule that we're applying here. We've got some division. So our f function would be cosine, and in which case f prime is going to be negative sine. And g is cosine of x plus sine of x. So g prime is going to be negative sine of x plus cosine of x, or cosine of x minus sine of x. All right, so let's use our quotient rule then. G f prime minus f g prime over g squared. This is a correct answer here. Not that you need to simplify it, but you could go ahead and distribute the negative sine of x and the cosine of x if you wanted to, but it says do not simplify, so go ahead and leave your answer. That is a correct derivative there. Okay, the third function, inverse tangent of x. So you've just got to recall then that the derivative of inverse tangent of x is going to be 1 over 1 plus x squared. All right. So in this case, instead of x, we have 1 over x, so there's going to be a chain rule involved. But when I first take the derivative of the exterior function, f prime of x is equal to 1 over 1 plus 1 over x squared. And because it's a chain rule, I also have to multiply by the derivative of 1 over x, which is negative 1 over x squared. Okay, and this I could put together here just to make it look a little bit nicer. It's going to be negative 1 over 1 plus 1 over x squared times x squared. Some nice work can happen there if you distribute that x squared, negative 1 over x squared plus 1. But again, that's a correct derivative there as well. And finally D, we've got a couple of chain rules embedded within this one. So the first thing is the exterior function. The most exterior function is something being raised to the 4th power. So I'm going to bring the 4 down, leave that something in there. That's not supposed to be, that's supposed to be e to the x. Okay, and subtract the exponent by 1. Okay, I've done that. Now I'm going to multiply that by the derivative of this interior function. And so this interior function has its own little chain rule. I'm multiplying by the derivative of ln of something, which is going to be 1 over that something. But I need to multiply that by its derivative, that something's derivative, which is e to the x. So I had 3 chain rules there. And I can just push this all together to make it look like one thing. So f prime of x is equal to, I now have 4 e to the x ln of 1 plus e to the x cubed divided by 1 plus e to the x.